Okay, in this video I'm going to tell you how do we analyze a design, right? Firstly, the design is made in a CAD software, and that CAD software's design is actually validated in Hypermesh and Abacus. Actual designing takes place in these CAE softwares, which are very much widely used in industries. Okay, so we are actually seeing a Hypermesh interface. Let me import a file for you. Okay, so right now I'm going to just open a file for you, and this is a drum, right? A water tank. Let's say you are working in a water tank company and your job is to design, optimize this water tank. So how are you going to do it? So all I can tell you here is that you can see a finite element model of a water tank here, right? And what are the forces that are acting on a water tank? Those are the hydrostatic pressure, right? That is given by rho into g into h. So this is what we are going to do. We are just going to see, fix this lower part. This is one of the boundary conditions that I have applied here. I have fixed all these nodes, right? Let me show it to you. See, all these nodes have been fixed here because in static level analysis you need to provide a boundary condition, and we will understand why do we need to provide boundary conditions as we go ahead with the course. All right, so these nodes have been fixed. ये सारे nodes fix हम कर चुके हैं, ठीक है. मटेरियल प्रॉपर्टीज हम दे चुके हैं. एसडीपी की हाई डेंसिटी पॉलीयूथैलिन की मटेरियल प्रॉपर्टी हमने दी है यहाँ पर, और एक प्रॉपर्टी. अब ये जो चीज़ है मैशिंग, ये 2D मैशिंग है. दिस इज ऑल 2D मैशिंग. दैट्स व्हाई आई हैव गिवन अ शेल प्रॉपर्टी टाइप टू इट. दिस इज all what we are going to learn here, right? Okay, now this model is completed here. This is what I am going to export, right? Okay, so I'm going to export it. Water tank 24 March. You can give any name to it. Save and use export. Alright, and now this is Abacus. Whatever finite element model that we make in Hypermesh, we solve them in Abacus because Abacus solver is really very strong. That's why it's always used in industries. So what I'm going to do is I'm going to just open a file. Okay, open. Whatever we had exported from Hypermesh, I have opened it here. All right. Which looks something like this. And in loads, actually I have applied a pressure, a hydrostatic pressure in this, and this is the reference or the origin with respect to what I have applied a hydrostatic pressure. Alright, that's all. And obviously this is the boundary condition. The lower nodes of this tank are fixed here. As we can see, they are all fixed. Okay, so finite element model is ready, the boundary conditions are ready, the loading is also ready, everything is ready in this, and this is what we are going to solve in Abacus. अब इसे हम यहाँ पर solve कर रहे हैं. I'm just going to run this job. Okay, I say submit and let it run for some time. Let's see. Okay, now the job has been completed. As we can see, this mark here completed, which means this is done. So I just visualize the results. Let us see how it comes. Okay, so this is how it is coming, right? See, okay, and it's uniformly distributed. I'm rotating the job You can see it's uniformly distributed, which it should be, right? So this looks like a good result, a very validated result, because whatever you run in Abacus, ANSYS, or whatever software you want to run, it will always give a result. So here you have to put your engineering judgment if the results are correct or not. As we can see, it looks like a good result. The bottommost points, they are having maximum stresses, right? And at the topmost points here, they are having minimum stresses. Red means maximum and blue means minimum. I just want you to think why the stresses in these points at the lowermost points are 0. Legend, set font, not 36, make it 18, apply. Okay, so the minimum stress is 1.59 into e to the power minus 13, which is 0, right? This is 0, and the maximum stresses are this one, 5.463 e to the power minus 3. So I'm just asking you why the stresses at these bottommost points are 0. I want you to think about it and come back with an answer. Alright, just think. That's what an engineer does, right? So this material SDP, high density polyethylene, is a brittle, not a brittle, is a ductile material, and according to von Mises theory, we are going to evaluate its failure. That's why we are seeing von Mises stresses. Alright, so what von Mises criteria says is that the maximum stress, if it exceeds yield strength of this material, which is 20 megapascals, it is going to fail. And certainly this is 5.46 into 10 to the power minus 3 is very less than 20 megapascal, which is the yield strength of this material. This is not breaking. So next part comes up the product optimization, because this is not breaking, this is not failing, right? So what we are going to do is, here we cannot remove the material from it, because this is a water tank. Once we remove the material from it, the water is going to flow out of it and it will be a useless product. Okay, then here I have mentioned 10 mm of thickness of this water tank. I'm going to reduce it to 5. Let's see what happens. Okay, and again I am going to run it here, submit. Okay, now this is also completed. Let me visualize the results, how they are coming up. So I'm going to come here, and as you can see, this is how the stress distributions are happening, and obviously the maximum stresses have gone up because we have reduced the thickness, right? And even at this case, it is much lesser than the yield strength of this material. So what will be the next point? We will further reduce the thickness of this and keep on reducing the thickness unless it fails. I hope I'm making sense here. Alright, and this is how product optimization of any product is done, and this is how an analysis of any product is done. I want you to understand that the design is actually happening inside CAE environment, because you would say that okay, at 2 mm it is barely breaking out because of water pressure. So please make this tank of 2 mm with the same diameter, with the same height, but thickness must be of 2 mm. These are the directions that you will give to a CAD engineer out there, and he will listen to you. Thank you very much.